Hello students and future mathematicians. Welcome to the first lecture of this calculus course. Now we're going to be spending a lot of time together and we have a lot to cover, so let's get right into it. First things first, this course is going to be broken up into two main parts. Now this isn't really that important right now to think about because we have a lot of time together and a lot of time to think about this, but I kind of want to just tell you what this course is going to focus on before we move on. The two main parts of this course are the following. The first part, we're going to be learning and finding and developing ways to find the slope of a curve at a point. And of course, there are many other subtopics and things that we're going to talk about in applications. But for right now, I just want to tell you about how this class is going to be broken up. That's the first main big chunk of this class, finding the slope of a curve at a point, how to do that. The second one, we're going to be learning how to find the area under a curve. So let's get right into it. Start at the beginning. The tangent problem of differential calculus. So hopefully at some point in your mathematical lives, before you got here, you learned about how to find the slope of a line. So we're going to review that a little bit before we move on. So if I just draw my axes here, we'll label this one X and this one Y. And if I draw a line, I know that I can find the slope of this line so long as I have 2 points that lie on the line. We'll put a point here. We'll call this one X1, Y1, and then we'll put a point here. We'll call this one X2, Y2. So in order to find the slope of a line, I need 2 points that lie on that line. And the components of the slope are the following. First thing I need to do if I want to find the slope of the line is I need to measure the vertical distance between the two lines. We call this delta y, or the change in y. And delta y is given by y2 minus y1. I find the difference between the y components of this line. The next thing I need to do is I need to measure the horizontal distance between the lines. So this is the vertical distance. Or the change in y. And the horizontal distance. Symbol that we use for the horizontal distance is delta x, or the change in x. In mathematics, this little triangle symbol means the change. We measure change by subtraction, so the change in x is going to be x2 minus x1. I find the change in x by finding the difference between these two x values. Now the slope of the line, you may have seen it denoted as m before, is given by the ratio of these two distances. Delta y over delta x, the change in y over the change in x. We call this the linear rate of change, or the slope. Now the cool thing about the slope of a line is that it's constant. The slope of the line doesn't change. No matter where I go on this line, if I pick 2 points on this line and I measure the vertical distance and the horizontal distance, and I find that ratio, it's always going to be the same. It doesn't matter where I find these 2 points. If I have another set of points right here, and I measure the vertical distance, and the horizontal distance, and I find the ratio of those two distances, it's always going to be the same. As long as I have 2 points that lie on this line, I measure these two distances and I find the ratio of these distances, that will give me the linear rate of change. That number is always going to be the same for any line. So we say the linear rate of change, or the rate of change for a line, is constant. The problem is that not all functions are linear. In particular, the functions that are the most interesting, in fact, aren't linear. Lines aren't very interesting. They're kind of boring in my opinion, but what do I know? I'm a mathematician. Some functions, as you know, are very curvy, actually. Hopefully you've seen this in some algebra class or some pre-calculus class. I can draw some other function that maybe looks like this. We'll call this function f of x, function of x. Now, if I try to do the same method on this function of x, if I pick 2 points on this function, and I measure the vertical distance, and I measure the horizontal distance, then what that will actually give me is the slope of the line that connects the 2 points. That's not the slope of this function, because I can pick another 2 points somewhere else on this function and do the same thing, measure the vertical distance and the horizontal distance. And I'm going to get some other rate of change. Notice how this line is a lot closer to the actual function than this one is. So I can do this all day. I can pick 2 points on this function, and I can draw lines in between them, and I can measure the vertical distance and the horizontal distance. And it's going to give me a different value every time I do it, unlike a linear function, which is not great for us. So that leads us to our first problem. We need to come up with a way to measure the rate of change for nonlinear functions. It's really easy to do it with linear functions because we can pick any 2 points we want and measure that vertical distance and horizontal distance, and it'll always be the same. But for non-linear functions, curvy functions, more interesting functions, it's going to be different wherever we put our points at. So this is what we're going to be developing in the first part of this class, the tools and methods to measure the rate of change for a non-linear function. That is the tangent problem of differential calculus. So before we can actually find the slope of a curve at a point, then what we need to do is come up with a way to approximate the rate of change at a point, or approximate the slope at a point. So go ahead and draw another plot here. We're going to do a pretty fun thought experiment with a function. Draw my axes again. Now consider this function. Again, we'll call this function f of x, give it a name. Suppose I have a point on this graph or on this function, we'll call it a, the point A. The point that's on this graph, this point A, is given by the x and y values, we'll call it a, and f of a. So this little a is actually my a on the horizontal axis. And this f of a is the height. If I evaluate my function at that little a, it gives me the height. So here's my height of my function. And my little a dictates where the height and how the height is found. So I'm interested in finding the slope of this curve at this point, or the rate of change of this curve at this point. Like I said, we don't quite have the tools to do this yet. So let's do the best we can with what we got. So, like I said before, in order to find the rate of change, I need 2 points that lie on this function. So I'm going to add another point. We'll call this point x and f of x. So this value right here, this little value on the horizontal axis is x. And if I evaluate my function at x, I get f of x. That gives you the height of this line. And what I can do then is I can actually connect these 2 points. I can draw a line between these 2 points. Is it going to give me a nice line? Whatever. We're just going to act like that line goes through that point. It turns out if I pick any 2 points on a curve and I draw a line connecting them, we form something called a secant line. This is going to be important for us to remember, a secant line. Again, this is found by picking any 2 points on this red curve or on any curve that we want. If I have 2 points, then I have 2 sets of x and y values. And if I connect a line, if I draw a line in between those 2 points, we form what's called a secant line. And the slope of the secant line, let me write it in the same color. Is given by the following. F of x minus f of a over x minus a. Now this might look a little bit familiar. Notice that my f of x and my f of a are my y values, y1 and y2. And then my x and my a are my x values, my horizontal values. So the slope of the secant line is just the change in the y value, or the difference in the y value divided by the difference in the a and the x values. The change in y over change in x. Now it turns out that the secant line will actually approximate the rate of change, will approximate the slope of the curve at the point A. Now, if we zoom in really closely, and we look at this, calculus is a lot of zooming in calculus, you can kind of see that this blue line approximates the slope of the red line a little bit. What's going on here? Stop it. But not quite, right? Like if I'm a person and I'm walking down this hill, it's a bad person. If I'm walking in this direction, I'm kind of walking downhill a little bit. You see that? You could say that I'm walking down this curve. But if I'm a person and I'm walking down this curve, maybe I'm a little bit happier, it's a little bit easier, or maybe I'm a little scared because it's quite a bit steeper. But as you can see, they're kind of the same. This red arrow kind of has the same slope of this blue arrow, but so it's an approximate. It's an approximation to the slope of the curve at the point. Not a very good one. We can certainly do better. So let's see if we can. Like I said, this will be a thought experiment. So suppose now that I can take this point and I can move it around. I'm going to keep this point fixed because this point A is the point that I'm interested in finding the slope of the curve at this point. I'm interested in finding the slope of the red curve at that point. So the only tools I have right now is I know how to find the slope of a line. So why not draw another line? Let me get rid of my 2 little happy people really quick. So like I said, I'm going to keep this white point A fixed, and I'm going to allow this point to move. So I'm going to move this point. I'm actually going to put it a little bit closer to this point A. And I'm going to draw another line in between those, and I can use that line as an approximation for the slope of the curve at that point. And it looks like it actually got a little bit worse, right? That's actually a worse approximation. This green line is a little bit steeper, right? A little bit more steep, and we don't really like that. That's not what we're going for. So I asked myself, can I do better? And again, this point can move, so I'm going to continue to move it up the curve, and maybe I'll put it right here. Now, if I draw a line connecting those 2 lines, well, that's actually a little bit better. You see that? If I zoom in a little bit better, now it looks like the slope of this yellow line is a little bit closer to the slope of this red line, which is something that's pretty nice. We kind of like that. Whoa, it doesn't like when I zoom in. So if I continue on with this theme and I say I can move this yellow point even closer, I can move it even closer and closer and closer. What happens if I take this yellow point and I just move it all the way as close as possible, as close as I possibly can to that white point, because that's the point that I'm trying to find the slope of. I'm trying to find the slope of this curve at this point. Now, all I need in order to find the slope of a line is 2 points that lie on that line. So if I take these 2 points and I move them infinitely close to one another, it looks like this line and this red curve have the same slope. We call that the tangent line. It turns out that the slope of the tangent line, or this last line that I drew right here, is the so-called instantaneous rate of change for the function f of x at the point x is equal to a. So in other words, I start off with a secant line and I have 2 points that lie on this curve, and I can draw a line in between those two, and if I let this point move and I take this point and I throw it up this curve as close as I can, notice that the closer I get to this point, the closer this point gets to the point that I'm interested in finding the slope of this curve at. If this point gets really, really, really close to that point, then the slope of the secant line is actually the same as the slope of the function at that point. We call that the tangent line. In other words, as I take this x value and I move it closer to this a value, as this value gets closer to that a value, the slope of the line in between those 2 points approaches something called the tangent line. Now we're going to talk a little bit about notation really quick. We don't really like to use m. M is really a linear notation. So the way that we denote the tangent line, or the slope of the tangent line, we say the slope of the tangent line is equal to f with this little tick mark. We call this f prime of a. F prime of a. And that is the slope of the tangent line, or we also call it the derivative of f of x at x is equal to a. Now, like I said, we don't really have the tools to find what that is yet. The important thing right now is that we just kind of understand the concept a little bit before we move on. So if I have 2 points that lie on this curve and I draw a line in between them, that's called the secant line. I can find the slope of the secant line using this formula. And the slope of the secant line is the approximate rate of change, or the average rate of change for this function. It's another way to say it. Average rate of change for this function in between 2 points is the slope of the secant line. If I take that point and I allow it to move, I allow it to move closer to that point A, and in fact, when it gets to the point towards infinitely close, when the distance between those 2 points, between these two values, is almost zero, I still technically have 2 points, so I can still technically find the slope of the line in between them. We call that the slope of the tangent line, and we call that the instantaneous rate of change at x, or for the function of x at the value a. In other words, as x approaches a, the slope of the secant line approaches the slope of the tangent line, and we call that f prime of a. Now, we're going to do a little bit of practice approximating the rate of change at a point for a given function. We're going to approximate the rate of change at a point for a given function. So let me zoom in a little bit so we can see this. This example says estimate the slope of the tangent line for the function f of x is equal to x squared at x is equal to 1 by finding the slopes of the secant lines through the point 1, 1 and each of the following points on the graph of f of x. So the point 2, 4 and the point 3/2, 9/2. Now I'm going to draw a little illustration so we can kind of see what this looks like. So I have my little drawing here, and I want to point out really quick before I forget that this is actually a typo. I'm going to do this point in yellow, and this is actually supposed to be a 4, not a 2. So this is the 0.3 9/4, and this is the 0.24. I'm going to do this one in purple. And I'm going to keep my anchor point. I'm going to call this my anchor point, the 0.11. I'm going to keep that in white. So I'm interested in estimating the slope of the tangent line for this function. This function is x squared, is a parabola at the point x equals 1 by finding the slopes of the secant line through the 0.11 at each of the following points on the graph. So the 0.24 and the 0.3 94. Now a function, as we know hopefully by now from algebra, a function is just an input and an output. So you know that if I put this x value into my function x squared, I'm going to get this y value out. 1 squared is 1. If I put this x value 3/2 into x squared, I'm going to get this value out. 9/4, right? My typo over here. And if I put the value 2, the x value 2 into this function, 2 squared is 4, so the second half of this point is 4. Now we're going to estimate the slope of the tangent line. We want to estimate the slope of the tangent line, which probably looks like this, the instantaneous rate of change at that point. And we're going to do it using secant lines. So I'm going to start with this purple point. So I'm going to take this purple pen and draw a line through these 2 points. We're going to pretend that that actually goes through that point. And I need to find the slope of the secant line at that point, the slope of the secant line. So the slope of the secant line is the following. What I do is I take my y values. Again, I take this vertical distance and this horizontal distance. To find the slope of this line, I need to find the ratio of these two distances. So the slope of the secant line for this function is going to be 4 minus 1. I take this y value and subtract that y value from it. Let me do it in white so you can see. And then I'm going to take the difference of these x values, so 2 minus 1. So the slope of this secant line, the slope of this purple line, is actually going to be 3/1, or just 3. So the approximation using this point for the slope of this line is 3. Now that's not a great approximation. Maybe we can do better. Could probably do better by taking this purple point and moving it a little bit closer to this white point, just like we talked about. Oh man, that's horrible. A little bit better. Okay, so if I want to find the slope of this yellow secant line, again, I'm going to take the difference between the y values. So I have y2 minus my y1, in this case is a 1. And then I'm going to take my x2, so 3/2, minus my x1, which is right here, 1. And if you did the work for this or put it into a calculator, you're going to get the value 5/2. So the approximation to the instantaneous rate of change for this function, f of x, at this point 1, 1, using this point here, is 5/2. Okay, let's move on. Let's do a more of an application type problem. We're going to find average velocity. So let's read this example. A rock is dropped from a height of 64 feet. It is determined that the height above the ground t seconds later is given by the function s of t is equal to negative 16t squared plus 64. Find the average velocity of the rock over in the given time interval. So a few things before we actually move on here. I just want to kind of explain what this function is giving us. This is a function of t, so a function of time. T in this case is seconds. We're going to be doing a lot of evaluating what our inputs to our function represent, especially when we talk about physical problems in this class. So what this function is telling me is if you give me a time in seconds after the rock was dropped, I'll plug it into here, and that will give me the distance away from the ground that it is at that time. So again, give me a time, I'll give you a height or a distance above the ground. And we want to find the average velocity. The average velocity in this case, so a physical interpretation of the velocity. Velocity is the change in distance over time. Change in distance over time. So this is going to connect really well to what we just talked about for average rates of change. We're going to give a physical interpretation to this. Now it says find the average velocity of the rock over the given time intervals. So what I'm actually going to do before I do anything else is I'm going to draw what this looks like. First thing I'm going to do is I'm going to draw a nice little time axis. So I'm going to call this horizontal axis time. And as time evolves, this rock is going to fall. And I have two different time intervals. And the first thing I notice is that they're both connected by this 0.5. That's real nice. So I'm going to go ahead and make that my point right in the middle. I'm going to say that this point 0.5 is the point right in the middle. And then I'm going to use other colors for these other 2 points. So I have this function, or I'm sorry, this time interval rather. This time interval is time goes from 0.49 seconds to 0.5 seconds. So a little bit under half a second to right at a half a second. So if I put that on my number line, this guy right here, 0.49 is that value. And then this one is the time interval half a second to a little tiny bit after a half a second. So I'll use a different color for that. We use blue here. So from 0.5 to 0.51. These are my two intervals. I have an interval from here to here and then an interval from here to here. And I'm interested in finding the average velocity of the rock over these given intervals. Now this function, as we probably know, is a parabola. So this horizontal axis is my time. I'm going to make another axis right here, a vertical axis. I don't want to do it in that color. I'm going to make a vertical axis that's going to represent height. Wow, it's horrible handwriting. This vertical axis is going to be my height axis. Now I'm going to draw a very rough sketch of what this function looks like. This is not what this function actually looks like, but we know it's a parabola, so it kind of has this shape to it. Okay, this is a very zoomed in version of this parabola. Okay, so in order to estimate the average velocity in between this time interval, for this first time interval, what I need is a point that's on this function. So I'm going to draw this point right here. And I'm going to say this is the point 0.49. And then in order to find, the height of the function at that time, I need to evaluate the function at that time. So I'm going to say s of 0.49. That's going to be my ordered pair. Same thing right here. I need this point. This is the point 0.5. And then in order to find the height of the rock at half a second, I need to evaluate this function. And like I said, you give me a time, I'll give you a height. Evaluate this function at 0.5, not 0.05, 0.5. And then finally, this last one. The t-value for this is 0.51, and to get the height above the ground and to evaluate my function s of 0.51. Okay. So to find the average velocity of the rock over this given time interval, I need to take these 2 points and connect them with a line. It's my first secant line, and I need to find the slope of that secant line. And then I'm going to take these 2 points, I'm going to connect them with a line. And I need to find the slope of that secant line. Those will give me the average velocity. So for the sake of time, I'm going to go ahead and just write out what these values are. And like I said, I need to evaluate this function at this time. So if I evaluate the function s of t at the point 0.49, what I'm going to get is 60.1584. In other words, if I drop the rock off of the height of 64 feet, whether it's a building or a mountain or whatever, If I measure the height almost a half a second later, I'm going to get about 60.15 or 60.2 feet above the ground. Now I need to measure the height of the rock at 0.5 seconds, so half a second later. If I evaluate my function at 0.5, I'm going to get exactly 60. So at half a second, my rock has dropped exactly 4 feet, because half a second after it's dropped, it's at 60 feet. That's what the interpretation of that is. So I'll go ahead and find the slope of this green secant line. So in this case, it's going to be the difference between these two height values. So I have 60.1584, and from that I'm going to subtract 60. And on the bottom, I'm going to have 0.49 minus 0.5. Notice that I kept these two values, 0.5 and 60, together. It doesn't really matter the order as long as those two values are kept together. And if I put that into a calculator, I'm going to get that this is equal to negative 15.84. And this value has units attached to it. Again, velocity is the change in distance over time. In this case, our function measures distance in feet. So this is going to be feet per second. This is the average velocity, so we're falling at a rate that's negative because we're dropping at a rate of about 15.84 feet per second in that time interval. Let's do the same thing for this time interval. The slope of this secant line, or the slope of the line that connects these 2 points, I'm going to do the same thing. I'm sorry, I forgot to evaluate the function first. I need to evaluate my function at this, so I need to evaluate s of 0.51. I'm not going to bother doing it for 0.5 because I already did it right here. I know that it's 60, so if I evaluate my function at 0.51, I'm going to get that value is 59.8384. So a little over half a second after we drop the rock, it's going to have a height of 59.8384 feet. And so the slope of this secant line, if I can do things in order, is going to be the difference of this height value, 59.8384, minus this guy, again, same value. And then over here, I'm going to have 0.51. Again, notice that I keep these two values that go together with each other, minus 0.5. And if I plug that into a calculator or some sort of, this is not supposed to be that, it's supposed to be a fraction bar. This is going to give me negative 16.16 feet per second. Now notice that in this time interval, a little bit later, about 1/10 of a second later after this time interval, we're falling faster. That's because our rock is accelerating. If I drop something from a height, it's going to start off falling relatively slow, not exactly slow, but it'll start off slow, start falling slow, and then it's going to go faster and faster and faster. We call that acceleration. We'll spend a lot more time talking about that. In this earlier time interval, we had an average velocity of about 15.84 feet per second, falling down. That's why we have a negative. And then in this next time interval, we're falling down a little bit faster on average, 16.16 feet per second. That's all I have for you for this lecture. I look forward to seeing you all very soon.